Given two arrays of positive integers ARR1 and ARR2. A prefix uses the leftmost digits of a number. 1 2 3 is a prefix of 1 2 3 4 5, but 2 3 4 is not. A common prefix of two numbers is a value that is a prefix of both. Only pairs with x from ARR1 and y from ARR2 count. Return the length of the longest common prefix among all pairs, or 0 if none exists. Example 1, ARR1 is 1, 10, 100, ARR2 is 1000. Pair 1 with 1000, shared prefix 1, length 1. Pair 10 with 1000, shared prefix 10, length 2. Pair 100 with 1000, shared prefix 100, length 3. That is the longest, so the output is 3. Example 2, ARR1 is 1, 2, 3, ARR2 is 4, 4, 4. No digit prefix matches between any cross-array pair, so the answer is 0. You are given two arrays of positive integers, and you need to find the maximum length of a common prefix between any pair of numbers. Your immediate instinct might be a brute force approach: take every single number from array 1, match it against every single number in array 2, convert them to strings, and count the matching characters. But when both arrays grow to 50,000 elements, pair-by-pair comparison explodes into billions of operations. Your code will time out. We need a way to search for prefixes without wandering down a brute force maze. To optimize this, let's look at the actual anatomy of a numeric prefix. If you have the number 1234, its prefixes are 123, 12, and 1. Notice what happens if we look at this through pure math instead of strings. Every time you divide an integer by 10 in code, the last digit drops off completely. By repeatedly dividing a number by 10 until it hits 0, we can extract every single valid prefix an integer possesses in a fraction of a millisecond. Instead of comparing pairs, let's build a master index. We take a blank hash set, our vault. We loop through array 1 exactly once. For every single number, we repeatedly divide it by 10, tossing every stage of that number straight into our set. Because a hash set automatically filters out duplicates and provides constant order 1 lookup times, we have just created a hyperfast, consolidated catalog of every single numeric prefix array 1 has to offer. Now comes the fishing phase. We loop through array 2. For each number, we check if it exists inside our prefix vault. If it is not there, we strip off its last digit by dividing by 10 and check again. The very first time we get a hit in our hash set, we stop. Because we are checking from the full number down to the single digit, our first hit is guaranteed to be the longest possible match for that number. We measure its length, compare it against our global maximum, and move to the next integer. While a hash set is incredibly easy to implement, there is an alternative structure built for prefix problems, a tree, or prefix tree. Instead of a flat set, every digit becomes a stepping stone down a path. Array 1 draws the paths. Insert 1234, root, then 1, 2, 3, 4. Array 2 walks down them until the trail goes cold. 1256 tracks through 1 and 2, but 5 dead ends. The shared path length is 2. Both approaches completely eliminate the brute force bottleneck, transforming a scary string problem into a clean, lightning-fast linear scan. Hash set on ARR1, 1, 10, 100. ARR2, 1000. The prefix set starts empty. Pass 1. ARR1 index 0, value 1. Digit 1 forms prefix 1. Add 1 to the set. Index 1, value 10. Prefix 1 is already in the set, skip. Digits 1 and 0 form prefix 10. Add 10 to the set. Index 2, value 100. Prefix 1, skip. Prefix 10, skip. Digits 1, 0, 0 form prefix 100. Add 100 to the set. Pass 2, scan ARR2. Max length starts at 0 and only updates on ARR2 matches. All 4 digits, prefix 1000 is not in the set. Drop the last digit. 3 digits 1, 0, 0, prefix 100 is in the set. Max length becomes 3. Return 3. A tree can do the same job in linear time. Implement that version yourself if you want the alternative. Let n be the length of ARR1 and m the length of ARR2. D1 is the total digit count across ARR1, and D2 across ARR2. Time is O of D1 plus D2, insert every ARR1 prefix once, then scan each ARR2 value from longest prefix down. Space is O of P for the prefix set, where P is the number of distinct prefix strings stored, at most D1. Function, longest common prefix length over all pairs X in ARR1 and Y in ARR2. Start with an empty prefix set. Loop over every value X in ARR1. Convert X to its decimal string S. For each prefix length I from 1 through the length of S. Add the first I characters of S to the set. Track the best answer, starting at 0. Loop over every value Y in ARR2. Convert Y to its decimal string S. Try prefix lengths from full length down to 1. If that prefix is already in the set, update best with the larger of best and I. Stop trying shorter prefixes for this Y. Return best.